Okay, so I'm going to start with a few general remarks about representations, smooth representations of p-adic groups. So the idea in this section is to just throw in a few keywords for those who are interested in looking further and just want an idea of the general story. So this is part 2 on general remarks, smooth representations of, and I just take GLN. Some of the statements that I will give are general for split groups or even non-split groups, but not all of them, so I'll be careful and I'll pick GLN over my p-adic group, p-adic field that I defined yesterday. There, general remarks. So my first observation is related to our last remark yesterday when I said, oh, there is no cuspidal representations for GL2FQ in characteristic P. Well, this is true. But in fact, they do arise for the p-adic group because we have two ways of inducing. I mean, two. We have more, of course, but that appear in this setting. And the first is the compact induction. So you take omega, an open compact subgroup, of G, and you look at the compact induction. Maybe I can add C in front of it, but sometimes I usually don't write a C, so I might forget it. Of a representation pi. This is the set of functions. Let's say the space is V. This is a space of function from G into V such that f of omega G is equal to omega acting on f of G. And since pi is smooth to start with, and the space is already, this is endowed with the action of G by right translation. And this ends up being a smooth representation. Okay, so the compact induction is left adjoint to a restriction. An example, if I take omega equals my Iwahari subgroup, and I consider the compact induction of a trivial character, this representation has infinite length. Okay, and the other usual way of inducing is the parabolic induction. So you take a parabolic subgroup, use Levy subgroup N, M, and unipotent radical N. Example, like we had yesterday, B equals T U. This is subgroup of G now, not of a bold G, not the finite group. Okay, and I take a pi V, a representation of M, and I will consider the parabolic induction from P to G of my representation pi. I keep saying P here. Okay, pi, this is pi. Again, I take the functions from G to V satisfying f of M and G equals pi of M f of G. But here, the action is again by translation on the right with this convention. But here I have to take the smooth part of this. Because not all such functions will be in the smooth part. So example, I take the parabolic induction from the Borel subgroup to GL2F of the trivial character. Well, this has two reducible constituents. over fp bar and over c, we have the trivial representation, a constant, and the quotient of the whole principal series representation by the trivial representation, which gives you the Steinberg representation. There, I just wanted to give an idea of how, that the fact that these two inductions are very different. This one has infinite length, this one is potentially reducible sometimes, and this one has two reducible constituents if I induce simply the trivial character. Okay, so now I work over C. So R, like yesterday, is the field of coefficients, and I choose C here. So what is the supercuspidal representation? And I'm not going to really look into details, the difference between cuspidal, supercuspidal. This is an irreducible representation of G that is not isomorphic to a composition factor of a strict parabolic induction of some for a parabolic subgroup which is strictly contained in G. Okay, and local Langlands correspondence tells us that roughly there is a canonical bijection between the set of isomorphism classes of supercuspidal representations and n-dimensional irreducible L-Deligne representations. Sometimes a fancy version of a Galois representation. Okay, so that's where we are at. Next remark, so that was my first remarks about supercuspidals. So yesterday we described some functors between representations and Hecker modules. So I'm going to tell you what is the equivalent in this setting of complex representations of the p-adic group. So I'm, like yesterday, I denote by rep Ci the category of representations of G that are generated by their Iwahara invariant vectors. And again, we have a functor sending a representation onto its I invariant subspace. And we get the affine Heck algebra here. Which is isomorphic, like we said yesterday, to an algebra convolution on the bi-invariant functions. Okay, and the claim is that, and this is Borel-Matsumoto theorem, that this is an equivalence of categories. Why is that? Well, yesterday we gave an idea of the proof in the finite case, and we needed to invert the cardinality of the group that we had here, which yesterday was a Borel subgroup, and here the Poe order of I is invertible in C, and therefore you have a Haar measure on G that gives measure 1 to the Iwahara, and using this Haar measure you can basically, it's harder, but you get the same kind of theorem as we saw yesterday in the finite case. Okay, so what is this Heck algebra, just as a remark? Well, we described it carefully yesterday, or a little bit more, in the finite case. And here, again, it has basis, well, the set of TW. For W, well, in the double cosets. And this time they're indexed not only by the symmetric group, but you have to add the diagonal part the lattices, and this is the extended Weil group in the case of GLN. And, well, the relations are roughly the same. You have the braid relations and the quadratic relations. And again, yesterday I insisted on the quadratic relations to tell you that when you work over FP bar, the quadratic relation becomes a little weird and tells you that when we'll work about FP bar, these elements that are here invertible in the Hecke algebra won't be invertible anymore over FP bar. Okay, in my remark, that was number 1 in my remark. Number 2, this subcategory here of the whole category of smooth representation is a block. By Bernstein, we know that the whole category has finite global dimension. Therefore, the Hecke algebra also has finite global dimension over C. So how are these two first remarks related, supercuspidal and this functor? Well, they're in fact kind of unrelated because so this category is made of several blocks, including this one, and this one happens to contain no supercuspidal representation at all. So if you look for the supercuspidal representations, don't look for them in this block. They will appear in other blocks. So by the theory of types, you know that, at least for GLN, all the blocks happen to be equivalent to categories of modules over Hecke algebra or tensor product of Hecke algebras. So in the case of GLN, the blocks of this category are very well understood, but again, no supercuspidal in this block. All right. So now a few remarks about what happens over FP bar. Well, yesterday, so we saw that the smooth characters of QP star with values in FP bars are tamely ramified or trivial on 1 plus PZP. And yesterday I spent some time explaining that in GLN or in GL2, you also had a big propy subgroup, the propy-Wahari. So likewise, you can prove that our lemma that was true for finite groups becomes the following thing. Any non-zero representation in the category of smooth mod P representation of G has a non-trivial propy-Wahari invariant subspace. Okay, there, so that was my first point. Yesterday in the finite case, this meant that there was no cuspidal representation of the finite group, but here there exist supercuspidal representations of G. Okay, there's a question of do we know a priori if they're admissible or not. I'm not going to go into these details. But basically what I can say is like they are mysterious. Except for n equals 2 and f equals qp. Sorry. Oh yeah, I mean, yeah, absolutely. Everybody has a pro-p Iwahara fixed vector, and some of them might even have an Iwahara fixed vector. Yeah. I mean, for GL2QP, there exists a superclassical representation with an Iwahara fixed vector. So this is really the exception. I should say that these have been classified by Breuil around 2000, and that's what I insisted on yesterday, thinking that, well, it's been 14 years, and we still don't know any other superclassical representation for GL3 or even... Okay, no. If F is different from QP, Pascual has computed superclassical representation of GL2 something else than QP. But we don't know if, I mean, and probably it's not all of them. Okay, so there. So now to continue the parallel with what happens with a complex coefficient, let's look at the functor. So we could work with the functor with Iwahara here, but since we said that every non-zero representation has a pro-p Iwahara fixed vector, we'll choose I1 here. And it makes sense to look at this thing. The same way as yesterday, I did not insist really on the situation where I picked the unipotent subgroup here. We mostly work with the Borel subgroup. Well, here, this is equivalent to taking the unipotent subgroup instead of the Iwahara subgroup. Okay, marvelous. This algebra is roughly the same as the as the Iwahara-Hecke algebra. Well, sorry, I shouldn't say this now. Yeah, sorry, this is FP bar. Well, let me say a word about this algebra here. So the fact that we pick I1 instead of I, well, we introduce subtleties, but you can overcome this subtleties. It's okay. Why? Because the quotient of I over I1 is just a finite torus, so it's not so complicated. The problem is like we picked FP bar instead of the complex number, and then what happens is basically the same as what happened in the finite case. The generators, the standard elements in the basis of this algebra are not invertible anymore because the quadratic relations become Ts squared equals minus Ts instead of the usual Q minus 1 Ts plus Q. Okay, so not only that, but this is not an equivalence of categories in general. It is an equivalence when n equals 2 and f equals qp. I think I don't have to mod out by the center anymore, right? Okay. Okay. Corollary of this. Remember that yesterday we said that the finite Hecke algebra had infinite global dimension. Well, we're going to deduce from this that this category, has infinite global dimension.
category has infinite global dimensions?
I mean, there are representations that have infinite projective resolutions and representation in this category, really inside of this category. Because it's quite possible that if I don't take that, in Pascuna's work, you see that, well, there is another condition here, it's locally finite, but in his work it appears that if you take locally finite representations here, the representation does have finite global dimension. So this is a strange result. Maybe it means that, it's probably a sign that this category is not the right one, or it's the right one and the situation is very complicated. But it does not mean that this one has infinite global dimension. Okay, and why do I claim this? Because I can prove that, and this is valid over any coefficient, well, the algebra of the maximal compact subgroup, which is isomorphic, to the finite Hecke algebra of the unipotent subgroup, not only it's a subalgebra of the big Hecke algebra over there, but it's a direct summand of you can take that if you want. We took QP, so as a left and right. As a bimodule. Well, that's quite general. This is not just for FP bars. This is not just for GL2s. This is not just for FP. But what matters is that this algebra here in general, we said yesterday, almost, that this one has, I actually didn't say it exactly for this one, but well, I guess if, I think we need P greater than 3 or something. Okay, and therefore, when this is a proof, this implies that this one has infinite global dimension. I guess if P is greater than 3, at least. So maybe here I need P greater than 3. Okay, so again, a big difference with what happens over C. Well, what about local Langlands correspondence? Well, I should have left that here. There is a one-to-one correspondence between supercuspitals of GL2QP. And well, here the natural object that appears is two-dimensional reducible representations of the absolute Galois group of QP. So there. That was already established by Breuil in 2000 when he classified the representations. But better than this correspondence is induced by a functor called Colmet's functor, or Colmet's Montreal functor, as I say. And this functor is not only, first it's defined as a functor for mod P representations given mod P Galois representations, but in fact, this is the functor that gives you the p-adic local Lagrange correspondence for GL2QP. A quick word, so this, the supercuspal representation of GL2QP, is quite hard to classify. It's a lot of calculations, and well, this is a lot of work. This is kind of easy to classify because the reducible representation of this Galois group are always going to be trivial on the pro-P radical of the inertia in the Galois group. So again, like, as I said yesterday, that sometimes working mod P makes your life easier. Well, on the Galois side, at least for the irreducibles, it makes your life a little easier. But then on the reductive group side, it's not easy. Okay, so that was my general remarks, I think. And maybe well, so overall, for other groups than GLN, very little is known except for a group with a small rank, SL2, U21, by people over here, Abdelatif and Kozio. SL2QP, also for SL2QP, you can see a nice one-to-one correspondence like that. So there is hope that for SL2QP things should behave. But overall, the general idea now is that GL2QP should be not, I mean, people used to think that, well, the mod P correspondence, do we have a chance to find something that is similar to the complex local Lagrange correspondence? And the first natural example to look at was GL2QP, and well, it seemed that it worked. But now the general spirit is more like, let's consider GL2QP as an exception and understand the general framework that is generic and in which GL2QP happens to be like a singular point. So the perspective on this program has changed in the last few years, and I guess that this term, this special semester, I mean, people involved in the p-adic Lagrange program are going to, I mean, think of that kind of thing, like define a new framework and stop trying to imitate what happened in the classical case. Okay, but part 3, I said that I would like to say a few words about the complex representations to give an idea of, well, the proof of a theorem, to give an idea of how you compute explicitly projective resolutions in this block, or not really this block, but I said that this category has finite global dimension. So how can you compute explicitly a projective resolution? And where or why does it fail when you change the characteristic? So this is based on a construction by Schneider and Stuhler, so coefficient system. On the building, and resolutions in the category of the representation of G over C and a little bit over FP bar. So everything I say here is based on 2 papers by Schneider and Stuhler. The first one explains deal with GLN, so basically we could just use the first one, and the second one is more general and goes further. Okay, so I'm just going to write the construction for GL2 because it takes less space, but it's quite general, and even for non-split groups. So this is what I called yesterday localization of a representation via coefficient systems on the building. So in fact, I'm just going to look at it on the tree. And first, I remind you that we attached certain subgroups to facets in the building. So when you take a facet of the building F, you can attach what I denote like that, the stabilizer of F in the semi-simple building. Then another construction, which for GL2 is quite easy, but in general it requires some work. You can attach to F a parahoric subgroup, which is open compact. And it's contained in the stabilizer. And then you can attach your pro-unipotent radical of the parahoric subgroup. And all this is compatible with the action of G, meaning that everything, like the pro-unipotent radical is attached to the facet GF, is the conjugate of the one attached to F, and likewise for the other groups. So example, even if we already saw them yesterday, so remember yesterday I had my tree. This is x0. I had x infinity here, and I singled out this edge. For example, we had a stabilizer of the facet x0 was kz. The attached parahoric subgroup is k, and its unipotent radical is k1. For PE, this is the Iwahari, and this matrix, the parahoric subgroup is just the Iwahari, and the unipotent radical is the pro-P Iwahari. And with this, I've described everything, because yesterday we reminded that the action of G on the vertices and on the edges is transitive. It's not true, I mean, for general groups and for a general facet, it might not be true if you don't take the vertices or the facet with the dimension 0 or maximal dimension. But for GL2, it's quite easy, and we described everything here. So now what does it mean really to talk about localization? Well, the idea is that we said that we'll study smooth representations, and yesterday I explained that it made sense if you study smooth representation to study them via their invariance under open compact subgroups. Well, here you have at each vertex and each edge you have a certain open compact subgroup, and you're tempted to study each time V invariant under something corresponding to this vertex, etc., etc. So this is what it's called. Well, this is what you do when you attach to V the following coefficient system on the tree to a facet F. So the coefficient system we're going to denote by V underlined twice. To a facet, you attach the invariance of V under the action of the unipotent radical attached to the facet. And this space is endowed with an action of the stabilizer of the facet. This is the first remark. And second remark, this coefficient system, first you need to describe the transition map, the restriction map. It's like a sheaf on the building. Meaning what? If I have a vertex contained in the closure of a facet, well, then what is the map from V IF to V IX? This is simply the inclusion. So you have restriction maps. And this coefficient system is G equivariant, meaning that those restrictions are compatible with the action of G. Meaning that you have a, well, how did I write this? Well, just saying that V, you have, okay. I mean, it's really trivial in this case because it's just inclusion. So those natural maps between the space associated to the facet F and the space associated to the facet GF are compatible with the restriction map. Okay, so you have what is called a G-equivariant coefficient system on your building. And it's quite a specific one. We really know what are the coefficients here. We gave them very explicitly. And the goal is to get from that to understand that via this process of localization, attaching to each space, to each vertex or each facet, a subspace of the representation, we can retrieve the representation itself. How does this work? By looking at the associated chain complex and looking at its C homology. So we have one-dimensional facets, zero-dimensional facets. So we need the one chains, the oriented one chains, and the oriented and the zero chains. So what are the one chains? So X parenthesis 1 will denote the set of oriented edges, out pointing or not. It's quite easy in this case to describe the orientation. And so the set of one chains, the oriented one chains, let me write it like that, is the set of functions on the set of oriented edges with values in the direct sum of all these spaces. And I want finite support, therefore the C here, compact support. And I need a condition. Well, I need that for any edge x prime, this is the vertices, with, let's say, x prime, f of the oriented edge f x prime is equal to minus f of the oriented edge x prime x, and this belongs to the corresponding coefficient at the edge. And this is naturally endowed with an action of G. GF at the edge G, what does this work? X prime is equal to G acting on F of X prime. So this is your action. Okay, so there. We're happy that it has an action of G, and it's actually a smooth representation of G, which is the good news because we are aiming at producing a resolution of V in our category of smooth representations. So zero chains, exactly the same almost. Well, this is the now X0 set of vertices. And there. It's the function on the vertices with values in this. With finite support. And f of x belongs to the corresponding space. and there's no extra condition. So there, we're good. And it's also endowed with an action of G that you can guess based on this. You raise x prime, and it gives you the action of G. Okay. All right, so we have the spaces of chains, of oriented chains. So we need the differential, and then we have our complex. So the differential from the space of oriented one chains does the following thing. If I take, let's say, well, x prime and edge, such that, let's say, x prime is outpointing and let f with support x prime, sending x prime onto this v, and x prime x onto minus v, then delta of f has support, is supported by the two vertices x and x prime, and it's easy to guess that delta f of x prime equals, let's say, v, and delta f of x is minus v. So this is a definition of the differential in the case of GL2. So I have a complex. Okay, and I'm going to write an augmentation map, and we can notice that this, in fact, as a space, and it's just the direct sum of all the V invariant under AIX for X of vertex. So there is a quite natural augmentation map here, sending a sum of elements here into their actual sum in V. And the claim, well, this is a complex here, and the theorem is that if V is generated by its, in fact, it's K1, I will write first I1. If V is generated by the I1 invariant, then this complex is exact. In fact, in the paper of Schneider and Struhler, you find if V is generated by K1 invariant, but I'm going to say a word of the proof in this case. So, and anyway, this theorem is just a level 0 case of this theory, because not all, as we said, not all representations are generated by their I invariants or K1 invariants. So if you want to get all representations, you need a smaller and smaller group here. I just do the level 0 case. Okay, so this is Schneider-Struhler. This is a level 0 case. Okay, as we said before, by Bernstein, we know that I should be able to build a a projective resolution for any representation, any complex representation of G. And well, if you pick V in a certain subcategory and you stay in this subcategory, I mean, this construction gives you projective resolution in certain subcategories. More precisely, so I look at the representation generated by their I invariance. Maybe I just need K1 invariance here. I don't know, I or K1, I'm not sure. I guess both work. But I will add a 1 here. Well, K1 will work anyway, because in the paper they don't worry about I. And I add a 1 here, meaning that it's all the conditions I'm used to plus V in this subcategory has, let's say, has a trivial central character. I could have just fixed this central character, but I just pick it trivial. Well, then, the claim is that this complex here, C1, is a projective resolution of V in this category. So it's not exactly so we have this condition on the center. So why is that true? Don't know if I have time to say it. I'm not sure I have time to say it. So, but the proof of this, the general idea is that this space here, for example, I just look at the space attached to 0. This one is slightly more complicated because it's less easy to see what representation it looks like. But this one is easy to see that it's exactly isomorphic to the compact induction over Kz of Vk1. And well, the fact that K1 is profinite and its pro-order is obviously invertible in C, and the fact that, well, K over K1 is finite, and Z doesn't matter too much because I'm in this subcategory in which the center acts trivially. This, that, and the fact that the compact induction here preserves projectivity, all this together, I mean, these arguments will tell you that this is a projective representation in our category here. Okay, so obviously this will fail in characteristic P. But more than this, it's not only the projectivity that fails, it's even the exactness of this complex, and I want to say a word about it by just mentioning how this theorem is proved. So proof of the theorem. Again, I'm just in the case where V is generated by its, let's say, I1 invariant or I invariant, or I guess let's do it in I invariant. Okay, it's a very poor, it concerns very few representations, but the idea is the same in general. The first step of the proof is proving the exactness of C1 when V is the universal representation attached to I here. If I change I will have to change the universal representation X, which is the compact induction of the trivial character of the Iwahari. And this is done in a paper over Z. This is just based on, it's quite intricate, but this is based on the contractibility of the tree, or more generally, the contractibility of the building. So for this, we don't care if we work over C or not. And then, so this, we get a complex. Well, let's say we get a resolution for X. Second step, well, we said several times that if V is generated by its I invariant subspace, then V, and we were in the right category equivalent to the Hecker module, and then we know that we can write V as this tensor product, and this tensor product, tensoring this tensor product is the adjoint of the I invariant vector, so it's also an equivalence of categories. This is a quasi-inverse. So this means that tensoring, let's call this gives us a resolution for X, I call it C2. So tensoring C2 by V1 over this gives an exact resolution to start with, because we have an equivalence of categories, and then you check that this actually gives you exactly C1. Okay, so there we have a resolution, and we even know that if you restrict ourselves to certain subcategories, we have projective resolutions of our complex representations. So what happens if you change the coefficients? Well, the universal part is still true. Meaning that the complex C2 that I didn't write, which is this complex but with the X instead of V, so C2 is still exact. But we can't tensor like that over the Heck algebra, except for GL2QP. As we said that for GL2QP, everything works. So we can tensor it, tensor the C2 by the I1 over HFP bar G I1. And we know that this is an equivalence of categories for GL2QP. And this, we get a resolution for V, which has no reason to be projective, because here all the arguments I used, I didn't show the proof, but all the arguments in this statement are really based on the fact that you work with complex coefficients. While here, well, this won't go through, but still you get a resolution. And well, first I thought I would have more time, and I could have explained to you how this resolution for GL2QP, if you look at the first pages of the paper by Colmez, in which he constructs his functor, he starts with finding for any irreducible mod P representation of GL2QP a resolution, a presentation that he calls standard, and in fact, this is exactly this resolution that you obtain here. So interestingly, the resolution you get is not exactly this one. I mean, this construction, I could have done it over FP bar, and even for GL2QP, this is not exact. Which is exact is for what is exact for GL2QP is exactly C2 tensored by this, which is not exactly the same thing. And well, it has, I mean, for people who make explicit calculations for GL2QP, it's quite important that this is not exactly the same thing. Well, I guess I would have had time to be more specific, but I think I'm going to stop here.